session. So if you're here for the transition from oil and gas, you're in the right place. If that's not what you're after, now's a good time to leave the room and find where you do want to be. My name's Eric Mackay, I'm at Edinburgh University, and I'll be chairing this session. So we've got four presentations this morning. We will have 10 minutes for each presentation, and then 5 minutes for Q&A at the end. And I'll let the speakers know when you're 10 minutes up, so you can please wind up as quickly as possible on that point. So I'm pleased to say we've got, first off is Rachel Adedokun from Robert Gordon University.
Thank you very much, Eric. Good morning, everyone. My name is Rachel Adedokun. I'm from Robert Gordon University, and this research I'm presenting to you is the third part of my PhD research. So this research is conducted in conjunction with Professor Peter Strachan and Dr. Anita Singh. And the title of the presentation is The Governance of Transition by Assessing Accountability and Transparency of Strategic Planning for Grid-Based Renewable Energy Development in Nigeria. First of all, I would like to define key terms I'll be using in this presentation. Governance of transition in the context of this research refers to the governance arrangement to facilitate and accelerate the energy transition process. And when I refer to grid-based renewable energy, I refer to it in terms of utility-scale renewable energy that fits into the national grid. Lastly, the strategic planning process refers to the route for developing and implementing renewable energy strategies, policies, plans, and projects. To set the scene of my research, I'm researching on the Nigerian electricity sector. And this is because 85 million Nigerians are without access to electricity, and the country is plagued with energy poverty challenges. Now, 35% of the urban area, which is in close proximity to the national grid, have no access to electricity. And this refers to both residential and industrial users. According to IEA 2020, data shows that as of 2019, about 4,000 megawatts electricity was supplied, but the demand was around 6,000 megawatts. That shows that there is, energy deficit there. Now, 75% of industrial areas are off-grid. That means they use fossil fuel-based generators to power their activity, which has been linked to high cost of production. Now, Nigerian population is projected to double according to the World Bank by 2050, and that simply means that the population, which is around 206 plus million now, would double, and then there will be demand for more energy. Now, the research problem, looking at it, the Nigerian government has embraced renewable energy to address some of these challenges, and I've looked at both off-grid and on-grid system. However, the off-grid system have achieved notable progress. However, the grid-based system, there's not been any success in that area. Existing research has found that the policy landscape, governance arrangement, and strategic planning process are ineffective. And they've also indicated that it's important for us to investigate the accountability and transparency challenges in the renewable energy policy execution. So it was critical for us to understand what went wrong and also to take on lessons learned. And existing studies have not really focused on accountability and transparency issues. And no research found has actually focused on the grid renewable energy system. Hence, our research looked at critically investigating the policy landscape and governance arrangement, particularly in relation to accountability and transparency of the strategic planning process of on-grid renewable energy deployment in Nigeria, and to offer recommendations to better understand how to foster transparency and accountability in the transition process. The objective was divided into four: to assess the level of accountability and transparency in governance and strategic planning process, and to evaluate the role of transparency in facilitating grid renewable energy development. Third, we looked at to investigate transparency mechanism to accelerate grid renewable energy development. And lastly, we looked at which actors should be held accountable for grid renewable energy development. So the theoretical underpinning was from accountability and transparency concepts. Accountability is all about holding actors responsible for their actions, agenda, and program, while transparency refers to the dissemination and access to information. Now, according to Ibrahim, transparency is one of the components of accountability. Now, based on Fox research too, he concluded that transparency and accountability has an overlap, and that clear transparency is a form of soft accountability. Now, the rationale for selecting accountability concept with transparency in this research is because we needed to achieve accountability and transparency in the grid renewable energy sector, and also to foster effective interaction between stakeholders in the energy sector. Hence, our research adopted this approach. Now, this research contributes to the accountability and transparency literature, and also builds on the debate of having an accountability design that factors in the specificity of the situation and also the context of the accountability. So we are building on this debate by applying it in the context of the Nigerian electricity sector and also in the context of Nigeria. So the methodology was that we interviewed 31 energy and non-energy actors. We interviewed directors, senior executive, policymakers in this domain. We went on to analyze our data using thematics analysis. And based on our result is based on the 4 objectives set out previously. So the first result was to understand the perception of the energy and non-energy actors on the level of accountability and transparency in the grid renewable energy space. Now, our finding indicates that the respondents indicated that some indicated that there was no transparency and accountability. Some stated that it's relative, and some gave affirmative, comments to the fact that there is transparency. And based on the quotes we have here, we could see it in terms of no transparency and in terms of affirmative transparency. However, it's important to note that because of the category of respondents I interviewed, because they were policymakers, regulators, ministries, government ministries, some of them categorically stated the fact that they can't state clearly if the system was transparent or not. And that was where we had things like very transparent, or I would say renewable energy, the level of transparency is high. But there's that caveat, stated before they went on to state this. In terms of the role of transparency in facilitating grid renewable energy development, respondents stated that it will help in the effectiveness and efficiency of the electricity system. And also they stated that it will foster education and acceptance of the actual cost of electricity generation and, electricity generation, especially from the end user's perspective, because presently electricity supply is highly subsidized in Nigeria. They also stated that it will encourage investment and boost business confidence, because part of the findings is the fact that investors are not coming into the electricity sector because of the existing challenges and transparency and accountability challenges there. Then they stated that it will foster good governance and also promote the growth of renewable energy development. Now, the third result stated that in terms of promoting transparency, that we could promote that by publicly informing the end users and the society about the activities going on in the grid renewable energy system. And also we could improve the metering system, which is roughly about 40% presently of energy supply or electricity supply to end users, and introduce a competitive bidding system which will boost transparency and improve the leadership and implement monitoring and auditing system. In terms of the perception of actors on who should be held responsible or accountable for grid renewable energy development, as we can see, respondents indicated various stakeholders, and some even stated all stakeholders, and some even indicated that there is no specific agency tasked with the responsibility of implementing grid renewable energy policies in Nigeria. And this is an extract just to show, some of the comments that respondents made. Now, in conclusion, transparency and accountability are below the expected standard and are crucial for good governance and in the transition of grid renewable energy in Nigeria. An agency needs to be established and tasked with the responsibility for grid renewable energy projects and initiative. And also there's need to encourage strong societal engagement and influence through participation in audits of the grid renewable energy initiatives and projects, and also demand information in order to boost transparency, which is presently lacking. There is need to also embrace hybrid accountability by introduction of top-down and bottom-up mechanism. So this is my recommendation to the Nigerian government, that they should set up an agency, and then the agency will be accountable horizontally to the NEMA, which is the Management Service Agency, and also to the regulatory organization, which is NEC, and then report vertically to the government, to the Energy Commission of Nigeria, and also to consumers. And this would also, they should also introduce audit and also rights to know or demand information initiatives in order to boost the transparency in the society. The limitation of this study is that I use a qualitative research approach. It will be good or improve, the output of this research if maybe survey could also be applied to this research. And also, I looked at solar and wind technology development, but this could also be extended to biomass and hydro, which is contained in the Nigerian Renewable Energy Policy. Area of further research is to investigate the relationship between transparency and accountability in the context of the Nigerian grid renewable energy sector, to see if there is even a relationship between them and how to foster that. Thank you very much for the time. And please, you can follow our work here. My LinkedIn and Twitter is here. Thank you.
Thank you very much, Rachel, for an excellent presentation. Thank you for sticking to time as well.
Yeah, thank you.
Floor is open for questions.
Yeah.
Could you please state your name and where you're from?
Yes. Hi, I'm Rebecca Grant. I'm a PhD researcher at the University of Edinburgh, and I look at off-grid solar systems in Rwanda. I was wondering, in your kind of comments on different stakeholders identifying with lack of transparency or agreeing that it was a transparent system, was that aligned to, I guess, stakeholder position? For example, people in government might be more likely to say that it was a transparent system, or those who weren't were like, was there any kind of correlation in terms of who said what?
Yes. Thank you very much. Sorry, I didn't catch your name. Rebecca, thank you very much. Yes, there was a correlation. So part of the finding was that most of the people, or most of the respondents that said, affirmatively that there was transparency, they were actually government officials. So, but the other populace, in terms of business owners, in terms of researchers, in terms of universities, and other stakeholders that I interviewed, they tend to sit between no or low, or even talk about, it's relative, they tend to compare to, okay, this other system too is not transparent, but to some extent you can say they're trying or something. So yes, you're right, government tend to, and that's why I said they always give the caveat of, I work for the government, so I would definitely say it's transparent.
Can I ask a question?
Yes,
so am I right in saying you said that 40% of electricity consumption is from the grid? Is that what you said? Did I get that number right?
No, 40% lack metering. So the present system, 40%, we just only have 40% metering system in Nigeria.
Metering, right.
Yes, metering.
Okay.
So that means end users are not metered. So houses are not metered. So they are charged flat rates. So you can actually track their actual consumption, and you can't bill them beyond what is the flat rate. So there've been this terminology called electricity theft, whereby, they circumvent the system in order to, be ahead of the system. And that's why my recommendation here was also, at the end of the day, this will foster or improve, this will serve as a surveillance, to hold society also accountable, because society also are very much part of the whole transparency and accountability debates, because of the significant role they play in terms of circumventing the system and in order to get their own way. Yep.
Okay.
Thank you.
Thank you. Any other questions? Okay, well, thank you very much.
Thank you.
So next up we have Arturo Regalado from the University of Aberdeen, and he's going to be talking about the effects of decline rate uncertainty.
Yeah. Perfect. Good morning, everybody. Thank you for joining this session on transitioning from oil and gas. My name is Arturo Regalado. I'm a PhD student with the University of Aberdeen and also sponsored by the National Decommissioning Center. And I will be speaking to you about my research on, actually I had to change a little bit because I just received some very good feedback. I'm having this as a journal article being now in peer review. And so I'm going to talk to you a little bit more of my research in more broader sense. And it's about modeling the decision to decommission oil and gas installation under uncertainty, a case study of the UKCS. For just those of you that do not know, decommissioning is basically this dismantling of all the offshore oil and gas installations, and it's currently one of the more important topics that we have here in the UK, especially going and transitioning from oil and gas to renewables. And just first of all, let's look at the outlook for decommissioning, which is very good news, especially if you're gonna get a job. There's a lot of money gonna be poured down to decommissioning. It's a very, very important activity. Only in this decade, we're expecting around 16 billion pounds to be spent in decommissioning, almost 1.5 billion each year. There's gonna be decommissioning of top sites, 125 top sites, 115 jackets. Almost 10% of the full expenditure in the UKCS will be on decommissioning, which is a very, 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 very big opportunity, but also comes with a very big challenge, right? Because the expected cost to decommission the full inventory of offshore oil and gas installations is around 45 billion pounds. And we need a way to actually decide on how do we cease production, when do we do it, and how can we secure the funding to make this possible. And this is where my research comes in. While in theory, there are many different aspects that affect or determine the decision to cease production and begin decommissioning, I am focusing on these three, which have to do with the oil price, because oil price in the oil industry is basically everything. It dictates the business cycles, but also financial security obligations. I was speaking about these costs, right? This 45 billion. And the thing here is that the UK has powers to request operators to have a separate fund or kind of financial instruments in order to ensure that they meet the financial obligations and the liability. And then we have also decline rates, which are the normal production profiles of the fields. They decline as they get old. We'll look at this in more detail later. And we have found that these are the main determinants of the decision to cease production. And my research question has to do with what is the combined effect of uncertainty in this oil price, decline rates, and financial security obligations on the decision to decommission. Let's go to some intuition first. Why is it important that we add kind of uncertainty to the mix? If we assume here we have a very simple discounted cash flow model here with the costs, and then let's see a revenue path. So if oil price is assumed to be fixed, that's a normal assumption when you're doing economics of these projects. You assume revenues to be fixed because at the end of the life, the reduction is declining and is now less. You have this very nice glide path that will lead to your timing of the decision of decommissioning, where your revenues are the same as your costs. That means you're getting to an operating loss or you're not making any profits. The problem is that we know oil prices can actually be low. And if the revenues are lower, and if this case happens, then we need to accelerate the timing of the decommissioning decision by, in this case, by 1 year, because now the revenues meet the costs 1 year earlier. But also we have the case that prices can go higher, right? Can go above the base case. And so you can actually decide to delay decommissioning. But these are very well-behaved lines. And in reality, oil price does not behave like this. It's something more like this, yeah? So how do we account for this uncertainty? How do we account for these oil prices? And how do we decide when to decommission? And this is very, very relevant because the decommissioning timing is essential for the government to make sure that decommissioning happens, but for the operators to make sure they actually can deliver the obligation and secure any supply chain work that it requires. And here comes the second part, the idea of the decline rates. Normally, a well-behaved field will have this idea of having an increase in production, plateauing, and then declining, right? Very, very smooth. But we know that in reality, there are below ground factors, for example, pressure, reservoir physics, also above ground factors like maintenance, that actually move the kind of glide path of the declining part of production. And we find there are actually in the literature 3 kind of models that better represent this. And you can see this for one simulation of an oil field, how the decline rate changes. And because it is production, it affects the revenues and again goes back and modifies these kind of paths over here. And finally, the last intuition is that of financial security and the COP, the cessation of production date. If we were just looking at fixing the revenues and having our costs, but we neglect the added cost of the securities because it's a requirement that can be done by the UK government, we will be actually saying, okay, you need to decommission at point A. But if we actually account for the costs, we see that the costs now meet the revenue path at point B. And this will be to a massive loss to the operator, and also leading to less value, supply chain disruption, because you cannot secure enough supply chain to actually make the decommissioning work. So it is a very, very messy stuff. And what happens is that normally operators do not count the security cost as part of this equation. So we need to also include that uncertainty into the models. The UK legislation accepts several different instruments, but in reality and in real life, we've seen that mostly the performance bond or the letter of credit or a trust fund are the more useful ones, and I have modeled them into my research. And let me just speak a little bit about the empirical strategy to assess actually and introducing uncertainty into this timing of the commissioning decision. And first, I use a discounted cash flow model that has been designed for 5 oil fields to be representative of the whole UKCS assets. I am using uncertainty and adding it by introducing Monte Carlo simulations, which basically means I am simulating 10,000, 15,000, 50,000 paths of each of these different oil price paths, production decline rates. I am then also adding different financial security instrument agreements and see how all of these variables actually impact a decision to decommission at the timing. I will spare you all the mathematics. If you want this, I can share you the slides with all the detail. But let's get to some of the results, please. So the main, I'm gonna just focus on some of the results. And here I am showing the different oil price modeling, the different oil price models, and contrasting them to this idea of having different financial security instruments, which can be no security, a letter of credit, and a trust fund. And here 3 models of oil price uncertainty that are widely used in the literature. And it may look like a very busy slide, but actually the key point here is if you read across the column, you will see that the starker or darker colors meet where the mean reversion process here of oil price is used. And also in each bar we can see more or less how many years of difference comes from the timing of the decommissioning based on a base case. And we can see that the mean reversion process actually adds a lot of uncertainty. So from all the models out there in the literature that can be used to model uncertainty, my research suggests that the operator can focus on using the mean reversion process because it adds a lot of uncertainty, so it gives you a wider range of options and opportunities. And also the mean reversion process has been shown to model oil price quite well. But the very important point here is that actually COP is very difficult to predict. We cannot know for certain when the COP date will actually happen. We can do a very broad or wide maybe uncertainty range around it, but we cannot know for certain. So we have to plan, and this is actually a very big problem, first for supply chain companies, because supply chain companies are basically chasing opportunities and trying to know which field will actually be decommissioned next, just to prepare all the work they need to do, the rigs, installations, plug, well up and abandonment. But also for the government, because the government then cannot know when the decommissioning is going to happen. So they cannot know if they need to issue a financial security notice. They do not know when is the operator going to engage in this. So by adding these tools, we can kind of solve some of this and at least give an uncertainty range that you can be certain that it will happen in maybe these 3 years. So you can get engaged with the companies early on. And finally, for financial instruments, it is very, very important because my research shows that financial instruments actually almost always accelerate COP, at least by 1 year. So when you add, or if you're the government and you require an operator to submit financial security, then you will basically be accelerating the commissioning by 1 year. And depending on the scheme, you can have one that will change in any kind of or size of the field, especially a trust fund. A trust fund is very, very disruptive to the operations in all fields. And so small projects are actually at greater risk of having distortions. Because for a big field, think about those fields that produce for 20 years, maybe 1 year is nothing, right? But for very small fields, 1 year can actually break the whole project. And if you're doing this assessment, then the oil field will actually never go ahead, even because you can break the economics just because of the decommissioning timing. And finally, very interesting, the decline rates actually seem to have a very nice, or well, it's not that nice because it's actually non-linear relationship. I'm still actually trying to work out why is this the case? And this is part of the research as my future work, because this non-linearity that's introduced for the kind of decline rates and the speed might have to do actually with also the modeling of the price, which I will need to do. And finally, the other part of the work I need to do is now, because the government decided to mess with my PhD, right? by introducing the new windfall levy and the profit levy tax, and apparently they're going to backtrack and actually change it again. So I have already modeled the new the new tax system, but they're going to already change it again and have it extended. So we need to have now a new tax system, which might actually be very interesting, because I expect it that it will postpone actually the decommissioning work, because the cash flows will actually be used in investment for oil and gas, because the windfall tax essentially also comes with an investment allowance, very, very strong investment allowance, that will suggest, okay, you know what, invest in oil and gas fields instead of decommission them. Interesting, we need to see what's going to happen there. And that's it, thank you very much.
So thank you very much, Arturo. Excellent presentation. Any questions?
Yep.
Interesting point about the need for stability in government to ensure that PhDs don't go on for
exactly.
forever and ever.
They will extend 1 year my PhD.
Thank you very much for the interesting presentation. So I'm asking about how energy security actually affects this decommissioning, because there has been this critical discussion when nations are talking about having to maintain the obligation towards climate change, that's having to transit from oil and gas, so that it should respond to climate change. But many institutions always cite the issue of energy security as reason why they should not just abandon hydrocarbon and all the oil fuels and move on. So does it, energy security, does it really affect or have anything to do with decision concerning this decommissioning?
I would say in this case, not that much. So for example, you can have, maybe you speaking about energy security as this need to actually continue producing. Maybe the kind of model, for example, if you were to use this uncertainty in oil prices, right? If you catch that the oil price path will be high for some of the fields and you decide to delay decommissioning, that may be the case for you. But there comes the other way around, because, for example, one part I'm not showing here is that, or especially in real life, is that most of the platforms that are going to be decommissioned are very old platforms, heavy emitters, very heavy emitters. So actually, what you will want is to decommission them as fast as possible, because their production, the share of production in the UKCS to the share of emissions is quite disproportionate. So their share in production is not enough to actually warrant having them emitting all the CO2 they are emitting, right? So you will want to have, okay, if I have all these models, you need to decommission and do this timing, and you have it now, so decommission now. Also now the government has this kind of idea of, we have this repurposing and recycling and reusing installations. You will see that a lot in this practice. But while that sounds very, very nice, most of the installations actually will have to be decommissioned. Not all the reservoirs can be used for carbon capture and storage, not all the top sites can be reused or recycled. So the default position of the government is to actually decommission and let's check what can be reused or repurposed. As such, I don't think actually energy security will play a lot of here, because most of this will already be producing at the very, very low end of their production profile. Yep.
Time for one more very quick question.
I have a question, sorry to command the mic. So Stephanie Mann from the ETP. What type of timescales are coming out in your models in terms of when decommissioning will need to happen in these oil fields?
Okay, well, this so because in my research I'm using the models from models that I have designed to be representative of the UKCS. I have used some of these to forecast some decommissioning outlook, and it appears that most of the decommissioning will happen maybe in the late 2030s, 2035s, 2030s. Especially depends a lot on the oil price. That's actually the key determinant. If the oil price keeps at these levels, maybe you can have very delayed decommissioning. But if you expect the transition to come forward, demand to reduce by 2030, oil price also reduces, and then you will be accelerating your decommissioning. So the time frame is actually quite uncertain. That's why these models are very good. But we have, especially for the UKCS as a whole, we have maybe a 5-year, 6-year range of uncertainty as to decommissioning timing.
Great. Okay. Thank you very much.
Thank you.
If there are any more questions for Arturo, maybe you could ask them at the end of the session. Next we have Sergi Arnau, also a colleague from the University of Aberdeen. And the title of his talk is Barrier Qualification Chamber. The floor is yours, Sergio.
Hi everyone. Thank you. Okay, so I'm Sergi. I'm an early career researcher at the National Decommissioning Center, working as a project manager. And today I'll be talking about the Barrier Qualification Chamber project. That is one of the big projects that we have at the moment. So the plan for today's presentation is to quickly introduce the National Decommissioning Center, who we are and what we do. I'll then give a brief introduction to well decommissioning. I'll give an update on the Barrier Qualification Chamber project, including project aims, design specifications, research topics, progress to date, next steps, and 5 minutes for questions at the end. So the National Decommissioning Center is a partnership between the Net Zero Technology Center and Aberdeen University. We are also supported from the Scottish and UK government. We are a research center in the context of oil and gas decommissioning, but a lot has happened in the last few years, and we've seen a shift towards renewables and energy transition. So even though our name appears the word decommissioning, we are doing a lot of projects related to offshore wind. To give you an idea of the partnerships that we have, we early this year we signed a partnership with the Offshore Energy Renewable Catapult to look at challenges around installation of floating offshore wind and the environmental impact of wind farms. And also early this year, we signed a partnership with the Nuclear Decommissioning Authority to look at cross-industry challenges, so how the two industries, oil and gas and nuclear, can work together to solve a common challenge. So for those not familiar with oil and gas decommissioning, is a growing market, as Arturo said. Well decommissioning only accounts for 50% of the total decommissioning cost. This is approximately £8 billion of spend in the next 10 years. There are currently 750 wells in suspension. These are wells that are waiting to be decommissioned, plug and abandoned. And this number will double in the next 4 to 5 years. So if we were to plug all these wells with traditional methods, and this is cement, using cement, it would take many years, in the order of 15 to 20 years working day and night. So it's obvious that we need better ways to do plug and abandonment. So by law, all wells need to be plugged and abandoned safely, or in other words, the capped rock needs to be restored so the well doesn't leak. Currently, wells are plugged using a 30 meters of cement plug, but the cement needs to bond well with the casing and rock, and making sure that this bond is good is timely and costly. So we think that cost reduction will come from collaboration with operators working together to provide joint scopes of work or campaigns to maximize efficiency, and from new rigless technologies such as bismuth alloys and thermite plugs, where smaller vessels can be used to carry out a P&A operation. I'll do this one first. So after we realized that the industry needed better ways to abandon a well, we saw the opportunity to provide a testing facility where new barrier materials could be developed, tested, and qualified. So the aim of this project is to mimic the well conditions, and this is high temperature and high pressure, to give repeatable and consistent testing conditions, to give operators and regulators the confidence that the new barrier material will actually work. The system we are designing, you can see it here, it's effectively a big pressure vessel that can go from the horizontal to the vertical, and therefore we can do incline testing. We can qualify a material to a specific standard. We can test with exothermic reactions inside the vessel, and we can do something called rock-to-rock testing, which I will explain in a second. So I'll do this one first. Okay, so the project was born having two aspects in mind. On one hand, we have the guidelines for qualification of new barrier materials and design standards, and on the other hand, we have the technology developers. So some of the things that the guidelines say, for example, is that to qualify a new barrier material, you have to pressurize it for at least 3 days and make sure that it doesn't leak. And or another thing is that you have to do cyclic testing. So if you are pressurizing the plug from below, you have to change it from above and from below again. And we had to make sure that the system that we are designing captures all these requirements. And another important aspect is the requirements from the technology developers. So for example, we've got Interwell or Bison that they've developed thermite plugs. These are very exothermic reactions that can go up to 2000 degrees Celsius, and therefore we need to make sure that the system that we are providing can cope with this type of reactions. Okay, so the design specifications for the testing facility are a maximum testing pressure of 10,000 psi. This is roughly 700 bar. Maximum temperature of 200 degrees Celsius. It's 8 meters long, is 20-inch internal diameter, approximately half a meter. We can use water and nitrogen to pressurize the seal, or both at the same time. The construction materials are alloy and carbon steel. We have a trace heating blanket around the pressure vessel to control the temperature. What else? It will have a control cabin, so the tests can be set up and operated remotely, and it's a portable testing facility. So apart from the rotating mechanism that I've already mentioned, the system has other functionalities. So on the horizontal position, the pressure vessel, the top end cap can be removed, and then you can slide into the pressure vessel what we call the test cartridge. The cartridge is what will simulate the well, and then the top end cap will have several ports, hydraulic and communication ports, that can speak with the test cartridge, and we, for example, we can pressurize specific regions of the well, or we can monitor temperature, pressure, or deformation during a reaction inside the vessel. So this slide shows some of the research topics that we think we can explore with this testing facility. So there are some numerical pressure models that have been used to simulate bismuth alloy plugs and thermite plugs. But again, these numerical models need to be validated with experimental data, and we hope to provide this with this testing facility. We can do rock-to-rock testing. So what would happen after a very energetic reaction? We would be able to check if the cap rock is damaged, for example, or any other part of the well where the reaction is not intended to work. Sorry. So we can also, another important aspect is the risk-based approach P&A. So as far as I know, this is a research being led by Heriot-Watt University, and these models again need to be calibrated and validated with experimental data that we hope to provide. And finally, after a test, the test cartridge can be removed, and you can analyze it in the laboratory and, for example, perform a metallurgic analysis on the plug. So where are we with the project? about 2 years ago, there was a FIT study. The cost of constructing this facility was very high, around £4 million. So therefore, there was a cost reduction study. At that point, we were able to secure £2 million funding for the construction. There was a stakeholder engagement where we revised the design specification, especially with technology developers, to make sure that what we are designing, it will be fit for purpose. We did the invitation to tender. The contract for the construction was awarded in February 2022. So the design phase is completed, and we are now starting with the procurement phase. So the next steps are really to engage with regulatory bodies to influence some of the guidelines and design standards, engage with industry to develop new barrier materials, and this system will be commissioned next year in Q3 2023. Thank you.
Thank you very much, and again for keeping to time. Any questions?
Very much for the presentation. I really enjoyed it. I have a question. Initially, when you started, you said if you use a cement method. Sorry, I'm not an expert in the commission, so the terminology might be a bit off. But yes, you said if you use cement, it could take maybe 20, even 30 years to fill up. Yeah. So this particular technology, based on the research done so far, how long do you think it might take to?
So usually to complete a standard P&A operation would take 5-6 days. For one well. So with these new technologies, you expect to use smaller vessels and go quicker as well, so in the order of 2-3 days. Yeah.
Can I ask you a question? I noticed you had Auburn as one of the companies involved.
Yes.
And they have a technology that actually invades into the pore space.
Yes.
So is your rig going to be able to address that?
These will come up to if we are able to reproduce the cap rock, which I know it's been done at a smaller scale. So the question would, the answer would be yes, if we can.
So could you also have formation rock itself?
Yes.
Permeable rock. And
yes.
Okay.
So the idea is to be able to have these represented as well. So the rock, the cement, the casing, the tubing. So we can do what is called the rock-to-rock testing. So we have a very energetic reaction here. Will the rock fracture, for example?
But will you be able to do experiments on a material that actually invades the rock?
If we can get to the right temperature and pressures,
yes. Okay.
I think so.
Yeah. Okay. Thank you.
But I only know that this has been done to the testing. It's a smaller scale testing.
Sure. Maybe chat to you afterwards if that's
okay.
Thank you. Okay. Well, if there are no more questions, we'll thank Sergey again. And the final presentation, I can still call it this morning, it is for another 5 minutes, is from Johnson Jimba. So Johnson, I think you probably need to load your presentation.
I've got 5 minutes.
You've got 10 minutes for a presentation because the session's extending till, but you may hear some stomachs rumbling because I think it's lunch. Is it not lunch next? It's lunch next, so you are between everybody and their lunch. I can tell you that Johnson's presentation is on the experimental investigation of the Coriolis meter performance under CCS transport conditions. And Johnson will be miming his presentation. No further introduction. Johnson, you're on your way.
Sorry about the time. So my name is Johnson, and I'm going to present just part of the experimental exercise of my PhD in the Harold Watt University. And my PhD is co-sponsored by ETP, the organizer of this event. I'm also co-sponsored by TUVSUD. They're also my technical partner as well. And my PhD is also part of the European-wide investigation of flow meters that we deploy for commercial CCS deployments. All right, so I'm just going to give, because it looks as though I'm probably the one having a very close relationship with people in CCS, carbon capture and storage, or carbon capture utilization and storage. So basically the idea or the underlying principle behind carbon capture and storage is that it is a strategy that even the UK government or the Scottish government are also looking at deploying to meet the net zero targets. And the idea is that we will capture CO2 from some of the hard to abate emission systems or stationary systems like cement plants, iron and steel, and some refinery as well. We will capture some of the CO2 from these plants. We will transport this CO2 to either an underground storage system or an utilization site. But then what I'm doing basically is my work is focused on the transportation side of carbon capture and storage. And because we know it will get to a point where CCS is going to be deployed in a large scale or in a commercial scale, so we will have to work, or we have to also, we need a system like meters that's going to represent a cash register, just like every other traditional industry like the oil and gas. So we will need to meter this CO2 for several reasons. For the business side of it, and also for environmental monitoring and reporting. So that's why we need accurate flow measurements of CO2 in CCS transport networks. So what I'm doing particularly is to investigate or gain more understanding on how you can meter CO2, because CO2 has a very challenging thermodynamic properties. So they can exist in different phases: the gas phase, a liquid dense phase, and supercritical phase. And because they exist in these different phases, it's difficult for you to, it is very difficult to meter them, unlike the traditional hydrocarbons that we have. And that's why we need to gain understanding, one, and we want to see or investigate what the existing flow meters that we have in the traditional industry. We want to see how well they are able to meter CO2 at the different transport conditions. And what I mean transport conditions could be gas, it could be liquid, it could be as a supercritical fluid. So we are starting, or I started with a Coriolis meter, what is called Coriolis meter. Coriolis meter is one of the popular meter that we use in the traditional oil and gas industry. We have other meters as well. And the idea is that we will conduct this investigation based on the existing maximum permissible error that we have that has been set out by different meteorological institutions. So we have them, like the EU, UK emission trading system. They have their own. They have a potential metering target that is required for every meter to meet. We also have other strict target as well. But what we are doing is we are setting even a stricter target, so that like 1%. And the idea is that we want to assess this meter based on this strict target, and our results will help us inform some of these meteorological institutions on what uncertainty limits they need to set for these meters, because this is CO2. It's not just only for the business. We are not doing it just for the business. We're also doing it for the the environmental implication as well, to cop some of the environmental implications. Okay. All right. Sorry. All right. So again, like I said, these are some of the flow meters that we have. Some of the popular flow meters that we have. You'll probably be familiar with some of them. Coriolis meter, that's what we are working on. We've got the orifice meter. Again, it's also quite popular. We've got some of the mechanical meters as well that we can potentially use. But the idea is that we want to start with those ones that we feel they have more industrial relevance. And that's why we are starting with the Coriolis meter. So again, Coriolis meter has a whole lot of advantage as well, and that's why we are starting with them. They are very good with directly measuring mass, unlike other flow meters like orifice that we know they measure volume flow rates. And the problem is that when you can't measure mass flow rate, you can easily have you can easily have disruption when there's instability in the line. And like I said, CO2 has a very funny thermodynamic property. So what that means is that when you have extreme weather change, it can potentially affect the phases at which the CO2 is being transported in the network, in the transport network. So that's why Coriolis meter can measure mass flow, direct mass flow. So it doesn't really have much effect when you have some of this instability. Okay, so again, this is just a simple principle of how Coriolis meter works. It works based on the principle of motion mechanics, like we know. So when you have these are the flow sensors itself. So when you have flow through the sensors, there's a vibration in the sensors. The sensors vibrate, and when they vibrate, there's a phase shift. When you don't have flow in them, the sensors are in phase. But as soon as you have a flow, there's a phase shift, and the time difference or the drift in this phase shift is what is equivalent to the mass flow, and that's the principle behind Coriolis metering. So again, we're not just metering, or we're not going to meter just pure CO2, because we are not going to get pure CO2. We will have some impurities in carbon capture systems. And what we did is to look at some of the potential impurities, and some of them that are quite, we have them in volume percent. So, and those that can potentially affect the transport condition of CO2, and that's what we have here. So what we did in the first mixture, we consider a quite lenient CO2 quality, while in the second one, we consider something like maybe the worst case. That's what we're going to have. That's what any transport or storage operator will allow through their line. So that's what we did here. So that's how we selected these two mixtures. And again, as an engineer, before you do anything, you want to model the thermodynamic property of that mixture. You want to see, okay, what happened, at what condition should I meter? So the thermodynamic modeling will help us to hypothetically know at what condition we should transport the CO2, and that's what we did here. So this is a phase diagram for a pure CO2. That is the phase diagram for the first mixture, the one that has just nitrogen. And what you're seeing here is, as soon as you have an impurity crept into the CO2 mixture, you have the liquid vapor boundary open up, and that means what happened is that you can potentially fall into the two phase. So instead of metering at single phase that you are seeing, you have an open up phase, so then you can fall into two phase. So you want to avoid that in metering. You really want to avoid that in metering. So that's why we do that. For the second mixture, you can see, because we have more aggressive impurities, so you see the phases open up bigger. All right. So, and what we did is we developed a novel gravimetric primary standard, and that's what we want to use to assess these meters. And for a gravimetric system, it's quite simple. So what you're just doing is you are transporting the mixture or the fluid from one point to another, taking the mass flow measurements of the fluid, and you're comparing it to a highly accurate weighing scale. And that's just the simple underlying principle behind the rig. And the rig has some specific features. So the weight scale we have in the rig is iso-calibrated. The pressure range is 2 to 100 bar. And the reason why we need to get to 100 bar is because CO2 at supercritical or dense phase needs to go as high as 80, 90, 100 bar. If not, you are not going to get to these conditions. And this is the condition at which we think we are going to transport CO2. So that's why it's also important for us to ensure that our rig can get to this condition. Then that's the temperature condition and the mass flow capacity, and importantly, the measurement of certainty of our rig, because it has to be 2, 3 to 4 times better than that of the meter. And particularly because we want to get to a liquid or dense phase condition, we need to execute this particular step in the transportation of the CO2, so which is a simple liquefaction process by compression. So what we are doing is we compress the CO2 in the vessel. At the same time, we subject it under cooling. Without that, you are not going to get to the liquid or even go to the dense condition, because the CO2 itself comes as a gas.
Johnson, can I ask you to move to your conclusions, please?
All right. Okay.
Thank you.
So, and that's the result we've got. This is for the pure CO2. We have the meter behave quite well. This is for the mixture. For the first mixture, again, we were very good with the, especially at the liquid and the dense phase. While for the last mixture, which has more aggressive impurities, you can see the errors started increasing. But the good thing here is that for Coriolis meter, we're still all within plus or minus 1%, and that's just the good thing we have. But what this means is that we can recommend to the appropriate body that probably we can reduce this uncertainty and go as low as 1%, because these bodies are targeting 1.5% or 2.5%. So what that means is that for Coriolis meter, we can go as low as 1%. But that will depend on what other meters is. So in our future study, what we're going to do is we're going to consider other meters as well. Like I said, this is a new rig. We already started building this. We are in the new rig. We're also introducing orifice meter into the network. And particularly, one of the things we are also going to be doing is we are going to be investigating these meters for what is called hightane. I know some of us might have heard of what hightane is. It's just a simple blend of hydrogen and methane. And this blend of hydrogen and methane is what the UK government think that maybe by 2025 we can start deploying to some of our homes. And that's one of the strategies to decommission the building stock. So that's me. Thank you very much. You can contact us.
I'll take one quick question, if they're ready.
Jun from University of Strathclyde Chemical Engineering Department. So very interesting talk. So my questions are regarding the CO2 mixture, measurement. So you mentioned about you have the curves. If you go back to slide 8. For mixing, you probably near the supercritical point. So you are expecting, for different species, you are expecting different supercritical point. Yeah. And when you have the mixing, how do you deal? So what the thermal fluid dynamics, for the mixtures. So for example, one fluid is one gas is already critical, past the critical point.
Yes.
The other one is not. So how it works?
All right. So thank you very much for that. So basically, for pure CO2, you can have it in different form. You can have it as the supplier can supply it to you as a gas phase, as a gas CO2, gaseous form of CO2 or liquid form of CO2. So it's quite easy to deal with. But when you start introducing impurity into it, the supplier, they are only restricted to supply you a CO2 mixture in gas form. So the idea is that we want to have something that we think we are going to mimic what the exact fluid that is going to flow through the pipeline. So what they did is they supply you the mixture according to your according to your specification. So because it's a CO2 mixture, it is technically impossible for you to supply a CO2 mixture in liquid phase. It is technically impossible. So that means the cylinders you are going to get are going to be a vapor withdrawal cylinder. Because if you supply the CO2 in liquid phase and the mixture in gas phase, what will happen is that the gas impurities will only form at the head space of the cylinder, so you are not having a complete mixture. So that's why this cylinder will come as a gaseous CO2 mixture. So, and that's where this compression has to come in, the compression by liquefaction under cooling conditions. Because it is at that point that you will be able to subject or condition the mixture to form a liquid CO2 mixture or a supercritical CO2 mixture. Without that process, it is impossible for you to get to, impossible for you to have your CO2 mixture in liquid, dense, or in supercritical phase. And this thermodynamic phase diagram that you have is what will give you a hypothetical idea of, okay, at what condition do I need to compress this CO2 mixture before I achieve this particular condition, supercritical or dense. So that's why we have to do this for every CO2 mixture that you are considering. Without that, you are not going to be able to achieve the conditions you want to achieve.
Can I suggest perhaps that if there are any other questions, or if you want to follow up on that question, we do that after the session, if that's okay. So thank you very much.